Okay, hi everyone. Welcome to another episode of Science and Technology History Q&A. It's been a few weeks since we've done one of these because the last couple of weeks, both of the Wednesdays of the last 2 weeks have been conferences that we've been organizing, which have had at least some historical content. But let me come back to some questions that have been asked here. Let me try and address them. There's a question here from Nelson. What appeared first in math, complex numbers or vectors? What's the relationship between them? Would the square root of negative numbers be a problem if equations were developed with vectors instead of regular numbers? Okay, that's interesting. There's a complicated story of the emergence of numbers and different kinds of numbers and so on. In fact, I was just at a conference this last week for a little bit that was talking about the general concept of numbers. And I just wrote a piece about, are numbers inevitable? And in the sense that I think I started the piece by saying, the aliens arrive in a starship. Is it inevitable that in order to make a starship, you have to have invented numbers? Or you go to visit some uncontacted tribe in some jungle somewhere. Is it obvious that they will have numbers? And the answer is, I think there are some things where there is a certain degree of obviousness about numbers and some where there isn't. But let's talk a little bit about numbers, the origin of numbers, and the emergence of different kinds of numbers like complex numbers. So one big question is, how do people ever come up with numbers? What was the origination of numbers? We don't know for sure, but people started making tally marks, maybe hundreds of thousands of years ago. There are bones with tally marks in them. There are sort of grim things like, the axe, which has a notch cut in it, but one suspects that was every victim of whatever kind of the axe got a notch associated with them. And that's sort of counting in unary, just representing successive numbers by just like 1, 1, 1, 1, 1 as you look at successive numbers. The question of when there starts being more non-trivial notation for numbers, that's a more complicated issue. And I think that's really the Babylonians are the folks who really started dealing with that maybe 4,000 years ago. There's sort of a question, how many times were numbers invented in the history of the world? It's just like we know writing was invented, 4-ish times in the history of the world with somewhat different writing systems. Were numbers invented only once because they all seem to kind of work more or less the same way, or were they invented multiple times? That's a question I don't think we really know the answer to at this point. It seems like all the numbers in the world kind of work more or less the same way. Is that a feature of numbers, or is that a feature of the fact that they were invented only once? Just like the languages of the world, they sort of, some of them are alphabetic, some of them are ideographic. They sort of have somewhat multiple ways of working, but some features are in common. But so, the origination of numbers was, what caused numbers to get serious, so to speak. I think one of the things I mentioned this in this piece that I wrote last week about numbers. If you are sort of out in the, just hanging out, living off things in the jungle or something, it's not completely obvious that you have to be a careful counter of things. Like, you have a bunch of dogs. Every dog has a name. It's like, you have 5 dogs. Well, I don't have 5 dogs. I have, this dog named this dog named this, and so on and so on and so on. Actually, I have to say, just as sort of footnote to that, I was curious about writing that statement about, this sort of way in which one might not need numbers. And I thought, just so I know what I'm talking about, let me, go figure out for so-called anumeric groups that don't, for example, have names for numbers in their languages, have only names for one and a pair and many and so on in their languages. I'm just curious, what do they call their pets and so on? And I then got dragged into the kind of the strange world of pet vocatives and the question of what you call, or animal vocatives in general. If you are living in one of these tribes, what is the typical, do you in fact name animals or not? And the answer seems, it's just like people might ask the question, do you name, cats and dogs? Yes, you do. Do you name cows if you're a dairy farmer or something? Well, maybe you do, maybe you don't. There's a question of when do you name things individually, independent of when you count them with numbers and so on. But anyway, so the answer is that it seems like anthropologists have studied pet vocatives, and that there are usually not individual names that are sort of distinct human-like names, but there are different words that are used when you address a cat, as opposed to when you refer to a cat. Referential name, is cat, but when you are addressing the cat, it's, kitty, kitty, kitty type thing. And I was somewhat interested to see there are big long lists of, if you are addressing a jaguar, this is what you say, as opposed to referring to a jaguar and so on. Okay, that's irrelevant, but sort of amusing. But in any case, the origination of kind of the idea of numbers and the idea that one could have things like positional notation for numbers, lots of stuff came in with the Babylonians, partly because the Babylonians, Mesopotamia was the place where sort of cities got serious for the first time, and people started having to organize things and have definite schemes for, property ownership and taxation and all this kind of stuff. And that led to kind of let's have a definite way of counting sheep. Let's have a definite way of having weights and measures, things like that, which drove the need for more sort of standardized representations of numbers and so on. And so, the Babylonians had this base 60 scheme that, we inherit through hours, minutes, seconds, and so on. And 360 degrees in a circle and such like. But that was definitely integers and some rational numbers. When they made tables of square roots, and there were square roots that didn't come out reasonably as rational numbers, they just left a blank there. They didn't really have a way to think about those kinds of numbers that were not representable in the integers in base 60 and some fractions and so on. Like the Egyptians had this scheme of every fraction has to be a sum of reciprocals. It's 1/2 plus 1/4 plus 1/7. It can't be 2/10 plus 3/100, et cetera, et cetera, et cetera. But as one looks at kind of what happened with numbers, integers, rational numbers, understood in antiquity. The concept of sort of square roots and things kind of understood implicitly through geometry and so on in antiquity, but I don't think really thought about as a thing for which there would be very clear notation and things like that. I mean, the ways that numbers got represented had tended to have a lot of geometrical entanglement. I mean, like I was looking last year at Euclid and trying to understand the empirical mathematics of Euclid and so on. And there are all these pieces in Euclid's Elements about, to compute the fifth apotomy. An apotomy is some kind of number that is representable as square roots in this way and that way and the other way. It's somewhat natural when presented geometrically. It's not particularly natural to us today with the way mathematics has developed, represented as in terms of kind of symbolic notation. But anyway, of course, there were weird other ways to represent numbers. Like, the Greeks had this way of representing numbers where they mapped numbers onto the letters of their alphabet. Alpha was 1, beta was 2, gamma was 3, etc. And with a number of, for somebody like me who spent my life as a computational language designer, there are some interesting little glitches that happened because, for example, they set their numbers mapped to letters at a particular time in the history of the development of the Greek language. And so that meant that letters like Sampi and digamma and copper, which didn't really make it in sort of later Greek writings, were burnt into the number system. And because you have to have a character that represents 60 or whatever it is, and it better be a character that's still there, so to speak, even if Sampi has been retired in terms of ordinary Greek writing. But so the Greeks used their letters of the alphabet as a way to represent numbers. Then Roman numerals, much better known, had this somewhat peculiar subtractive mechanism where, 9 is ix and things like this. One of the things that is sort of a long-term notation matters type story in the history of mathematics is, I think, the invention of algebra was slowed down by centuries, millennia perhaps, by the fact that people represented numbers using letters, that the Greeks had their scheme, the Romans had their scheme, for where you're fundamentally using letters of the same kind you use in words to represent numbers. Because if you wanted to represent an unknown, an x, well, you wrote down an x, but that x looks just like the x that represents 10 in the Roman numeral system, for example. Euclid had already labeled, I think, angles. It's not clear if Euclid actually drew these figures or if they were somewhat later, but within the Euclidean tradition, people had drawn figures in which they labeled angles and things with letters, with Greek letters and so on. But for some reason, that as a matter of writing down equations and things like that, that didn't really happen. So it was, then there was the whole Hindu-Arabic numeral system, which existed in those parts of the world and was brought to the West around 1200 AD, primarily by Leonardo Fibonacci, who wrote this book, Liber Abaci, the book of the abacus. I mean, in those days, it was sort of a big business to be a consultant for merchants, a mathematical consultant for merchants, and that was what Fibonacci was. And people would write these books that had titles like, The Secret Way of Doing Calculation, that would allow you to compute things that you needed as a merchant, and much better than all those other merchants over there. It's kind of got quant finance version 0.1 or something. So in any case, once there were Hindu-Arabic numerals, there was a different notation for numbers as from letters of the alphabet. And so letters of the alphabet started to be able to be used as unknowns. And that was a thing that kind of came in with people like Vieta in the 1400s, I guess, starting to bring in ideas of algebra and so on. Because people had like Diophantus in the first century AD had perfectly, had written these books about equations, notably about Diophantine equations involving integers, but he'd written about other kinds of equations. But his equations were always written in terms of words, and they were not written in a kind of mathematical notation. But that started to come in. Now, it's still the case by the 1400s, there isn't there aren't negative numbers. People are not talking about negative numbers. People are barely talking about zero. And there certainly aren't complex numbers. And the thing that the camel that broke the hair, that broke the camel's back in this case, was the cubic equation. So people knew that even in antiquity, people had found out how to solve quadratic equations, x squared, ax squared plus bx plus c, and had found the quadratic formula. Cubic equations, x cubed, etc., much more complicated. People hadn't been able to solve the cubic, and particularly they hadn't solved the casus irreducibilis of the cubic, where you would have and there's sort of the question of, is there a solution to the cubic that involves real numbers or not? And there you can have with a cubic, you can have one real solution, two complex solutions. You can have, with real coefficients, I don't think you can have all complex numbers. Anyway, so we now get to the end of the 1400s, beginning of the 1500s, and people were sort of struggling to solve the cubic. And this chap Cardano, what's his first name? Guglielmo Cardano, forget the first name. Cardano, before it was the fourth most valuable cryptocurrency, Cardano was a person who lived around 1500, who was primarily a doctor and also various other things in those days, as some of us aspire to today, to be somewhat generalists. In those days, that was more of a thing. Cardano was both a doctor and an astrologer and a mathematician and probably various other things. Notably, he was also a big enthusiast of personal analytics. He recorded all these different facts about himself. And that was a thing that people did in those days is let's recognize when something good happens in our life, is that correlated with the phase of the moon, with the position of Mars in the sky? Is it correlated with this or that or the other? And people would kind of record this personal analytics data in the hopes that if they could correlate that, for example, for their own lives, they could then essentially become consultants where they would say, well, let me look at what it is for your life, then I can predict whether you should do this or that, make this or that business decision or whatever based on that. Famously, Cardano is said to have predicted the day of his death. I don't know if that's really true, but I think he has an autobiography which begins something like, all the good things that have happened to me in my life happened when it isn't a full moon, but it's some other astronomical situation, so to speak. Anyway, Cardano comes into this, and there's this cubic equation to be solved. And there were a number of other people. There's a whole tale of woe associated with a person called Tartaglia, another person called Piero da Ferro, I forget. Oh gosh, I'm not sure. But anyway, there were these three people, and they had complicated relationships. One was a student of another, and one was some relative of another one. Anyway, all these people were kind of battling to be the one to give the grand demonstration of I can solve the cubic equation. The one who became most famous for doing that was Cardano, who wrote this book called Ars Magna, the Great Art of Mathematics and so on. But what did he do to solve the cubic equations? It turns out he needed two ideas. He needed negative numbers and he needed complex numbers, imaginary numbers, square root of -1 and so on. And so very bizarrely in the history of mathematics, those two ideas that are taught so separately today when we teach elementary mathematics actually arose in mathematics, became accepted in mathematics around the same time. And both as a result of this fairly elaborate thing, the cubic equation. So that was kind of the, negative numbers got serious at that time. So did imaginary numbers. That was long before the invention of things like vectors. The fact that we can interpret complex numbers as being numbers, where there's a real and imaginary part, and those are like points in a two-dimensional plane, that idea long postdates the original invention of imaginary numbers by around the time of Cardano, around 1500 and so on. That whole idea of sort of the mapping of complex numbers to these points in the plane, I think that got big with people like Euler in the 1700s. But again, Euler wasn't drawing, I have a copy of Euler's collected works, a very impressive, whole shelf of opera omnia, all the works of Leonhard Euler. Very impressive and very interesting to look at because their notation is very, very modern. I mean, they would be completely at home in a modern calculus course, so to speak. Euler was the one who, for example, introduced, certainly pi, I think also I. Pi there was a chap called Jones in England who had come up with the notation for pi, but Euler is the one who cemented that notation and really used it widely. But by the time of Euler, people were understanding, there's this notion of, e to the I theta and all this kind of thing. And there's some kind of geometrical correspondence of complex numbers. But the notion of vectors didn't come in until much later. I mean, the notion of matrices, which seems to us very obvious, vectors, matrices, all those kinds of things, linear algebra and so on, that was a thing of the very late 1800s. I mean, it came in through a lot of weird theories. I mean, there was the theory, so-called determinant theory, that was a big thing that was looked at. Well, so for example, Arthur Cayley was the person who eventually introduced basically the idea of matrices, and that was, I think, in the 1880s, maybe 1870s, perhaps. And Cayley had been looking at solutions to equations and whole sort of the structure of symmetries of equations, all this kind of thing. And that led to both this representation theory and, so-called invariant theory, which was a whole branch of mathematics that sort of was related to things like group theory and so on, and related to algebraic geometry in the end. But it was a kind of a big thing in the late 1800s. But so this notion that now seems completely obvious to us of these arrays of numbers and things, that was a completely unobvious notion back in the time of when that was being invented in the late 1800s. And I should say that if we look at this kind of span of history, the idea of imaginary numbers, negative numbers, 1500-ish, the idea of decimal numbers, of, we can represent what we now call a real number, something the computer will be 0.72564, et cetera, et cetera, et cetera. That didn't come in until the mid 1600s. And what happened there was there was a chap called Baron Napier, a Scottish baron, who basically invented logarithms. And in particular, he invented the idea of so-called Napier's bones, which became the basis for the slide rule, where the idea was if you mark if you have this this pair of ruler-like things, and you mark off the numbers logarithmically, then you can just, when logarithms add, the numbers multiply, and so you can have it be the case that you just move one of these sort of ruler-like things relative to the other, and that will give you multiplication. That's how slide rules work. There's a chap called William Outred, I think, who invented slide rules in the 1600s. And I, as a young child, sort of independently invented the addition slide rule, a rather more elementary idea where you literally take two rulers and you can slide them relative to each other, and that will make you an addition slide rule. As when I was rather young, I think there must have been teachers who were very confused about why in doing math exercises I was always there with two rulers. But anyway, we'll leave that as a somehow these things, one never really changes what one does. It was always, tools for solving things has been my kind of lifelong activity. But in any case, the idea of kind of number lines, marking things off, decimals, the logarithms come in. There's a guy called Simon Steven in the Netherlands who was, I think, generally gets credited with the idea of actually, decimal numbers, write down the digits, point, blah, 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 blah. Not quite the same as the Babylonians or the Egyptians and so on, who'd had these rational fractions and so on to represent fractional numbers. But in any case, the thing, so I think the question that was asked was, how do vectors relate to the invention of complex numbers? Vectors came centuries after the invention of complex numbers, and the sort of the standardization of vectors as a thing you really looked at. I mean, even when I was a kid, so this is, I don't know, 1960s or something, the math books did not routinely talk about vectors and matrices. The elementary math books would get to calculus, they wouldn't have talked about vectors and matrices by that point. I think what happened is in the kind of the flowering of linear algebra, particularly happened it happened in pure mathematics, but it also happened in the world at large in the 1960s when people started to be able to numerical linear algebra on computers, and the idea of arrays on computers was quite natural, and arrays of arrays which made matrices, and then this whole development of all these methods for finding inverses of matrices, solving matrix equations, all that kind of thing. That was the 1960s to 1970s. That really happened in a way that is very reminiscent of what's happening with modern machine learning. It was just a bunch of very detailed, specific, often sort of hacky seeming algorithms that, by golly, went from, it was really difficult to solve a system of linear equations to it's completely routine. It can be burnt into the hardware of an FPU or something, floating point unit, or it can be built in, and it became something that was very efficient to do. And then a lot of things got built on top of that in computer graphics and other areas and so on. So the kind of something like vectors that seem very obvious to us today were not obvious in the history of mathematics. Nobody was using them. Nobody cared. That wasn't the point. I suppose coordinates did come in. People like Descartes, for example. We have the Cartesian coordinates, Cartesian coordinates because they were invented by Descartes. I don't completely know the relationship. I'm trying to think about this. People drawing geometrical figures where they had computed the points and were drawing them on a coordinate grid. I don't think that comes in. I'm not immediately remembering. I'm not remembering seeing Euler doing that. I'm I suspect by the time of Gauss in the 1800s that was being done, but I'm not sure. I think yeah. So those are that's a little bit on the subject of kind of the origination of the notion of complex numbers, and then it's worth realizing that people invent new kinds of numbers every so often. Like famously, William Rowan Hamilton invented quaternions in the 1840s, maybe 1847. I vaguely remember. And there's an Irish chap who was famously, out and out walking, or maybe on a horse. I'm not sure. I think walking, and suddenly has this idea for how quaternions should work. Quaternions are hyper-complex numbers. Instead of just a single square root of -1, there's ijk, which represent, there's one ijk, and you can represent these quaternionic numbers using that. And he was so proud of this, he kind of carved the key relations for quaternions in the side of a bridge, which I think is still visible today. But hopefully nobody would say, "Oh my gosh, that's terrible! Graffiti, vandalism, etc., etc., etc." Mathematics is lost forever as a result of that. But in any case, I think that quaternions were, for a while, it's like, oh, everything's going to be quaternions. Quaternions are amazing. We're going to define quaternionic physics. We're going to define everything's going to be quaternions. Didn't really pan out that way. Quaternions are actually a useful representation of rotations in three-dimensional space, and they're interesting, but they're not kind of the take it away, that's how everything works. Unlike complex numbers, which have turned out to be really pretty central to lots of kinds of things. You can go beyond quaternions. You can go to octonions. That's as far as that type of Clifford algebra. No, oh gosh, I'm trying to remember. It only goes as far as the octonions with certain properties that you need. I mean, the quaternions no longer have commutativity of multiplication. The octonions no longer have associativity of multiplication. But octonions, again, kind of a special kind of number that haven't turned out to be very globally important. So it's always an interesting thing where you see these different sort of kinds of numbers or kinds of constructs in mathematics. Are they going to be globally important or not? Another one that came in late 1800s was transfinite numbers. That was Georg Cantor's idea. And it's sort of an interesting piece of mathematical history. I mean, Cantor was trying to solve a very practical problem. He was trying to look at the sums of trigonometric series. You say sine 2x plus 1/3 sine 3x plus 2 times sine 4x plus whatever. You have a trigonometric series like that. And the question is, when you do the sum for an infinite sum of that kind, for sine nx times some coefficient, summed for all n, does that series converge or not? And the domains in which it converges can be very, very elaborate. And so what did Cantor do? He tried to make a description of the sets of values for which there is convergence in the trigonometric series. What mathematics did he have to do that? Well, he had to invent it. It was called set theory. And that was how set theory came to be invented. And transfinite numbers were invented at the same time as part of this story of this very practical thing about finding the convergence of trigonometric series. Subsequently, Cantor kind of said, let's consider transfinite numbers separately. Let's consider set theory separately. And those became, well, set theory became a very foundational theory that people sort of have often believed is kind of the most foundational axiomatic theory for mathematics. Not sure if that's really right, but that is the general belief. Transfinite numbers did not have such a happy time. Transfinite numbers are they're the numbers you get. For example, the ordinal transfinite numbers are the numbers you get. You count 1, 2, 3, 4, 5, and you keep on counting forever, and then you say, what's the number after what you get to if you count forever? Well, let's just call it omega. Then you can say, well, what's the number after that? What's omega plus 1? And you can make up a whole theory of transfinite numbers. You get omega to the omega, you get limits of omega to the omega to the omega to omega, call that epsilon 0, and then you get limits of that. And you can build this whole world of transfinite numbers. And the question is that useful for anything? And the answer is, in 100 years, it's been kind of marginal. It's been useful for some things. It's pretty interesting. It's mathematically interesting. The structure is interesting. But if we say, does that relate to the physical world? Well, actually, our current theory of physics kind of suggests, the theory of physics that we developed in the last year or so kind of suggests that transfinite numbers don't really have a place in our instantiatable physical universe, but they're nevertheless things you can study as conceivable kinds of things. But in any case, that's an example of, I think it's just an interesting feature that, Cantor discovered something like set theory. But by the time in the 1960s, there had been this effort in mathematics education that was called new math. And I'm sure there's been a new math many times in history, but the new math was supposed to be sort of rethinking of what elementary math should be like. I mean, elementary math, in the textbooks, you can see what the Babylonians taught as elementary math. Much of it is quite similar. The kind of word problems the Babylonians had are bizarrely similar to the word problems that that we have, that people solve today. And if you go through history, by the 1600s, the first kind of somewhat organized math curricula, there was one, I think it's Christ's Hospital School in England, if I remember correctly, was the first place that really had a sort of organized math curriculum in that sense. And they brought in some consultants, this was in the 1600s, they brought in some consultants to help define this curriculum. And one of those consultants was Isaac Newton. And so they got some calculus in their curriculum as a result of that, or at least Fluxion-based calculus, perhaps. But in any case, the sort of time rolls forward, and math textbooks, they kind of standardized in the way they standardized in the 1800s and to 1900s. And there was this kind of idea, let's make a new math, because this is not the right, doing arithmetic and things like that. Oh, that's old, let's do something new. And by that time, kind of things like the Bourbaki school, the French school of very pure mathematics, had come and been around. And so people had this idea, mathematics is really something more than just doing arithmetic and so on, more than just doing algebra. Let's bring in new math, which brings in the concepts of more advanced mathematics. So the result of that was actually in the early 60s. I guess the mathematics teaching profession was a lot smaller than it is now. There was some, maybe 62 or something, there were these conferences at Harvard, I think, that were sort of defining the new math and defining what the curriculum should be. And that led to a curriculum that had as one of its front and center features set theory. And so this thing that had gone from 1880s or whatever, this very obscure thing with transfinite numbers and all that, by 1960, it was, let's teach this to all school children. And I remember when I was sort of learning math, I wasn't a particularly good school learner of math, but this must have been 1969 or so. The textbooks all got sort of replaced with new math textbooks that had set theory and topology. In a sense, and set theory is about intersections and unions and all this kind of thing. And topology was about donuts and holes. Well, actually, I grew up in England where donuts don't have holes in them. So that the topological concept of a donut with a hole sort of wasn't really a thing. They were just donuts, at least when I was growing up in England, were just these things that had jam in the middle, but the jam was injected into the middle rather than there being a hole in the middle. It was just a thing homomorphic to us. In any case, well, let's see. Okay, there's a whole bunch of other questions here. Actually, there's a question from RBS. Real variables, rational numbers, analysis, why not just stick to integers? Maybe I shouldn't get too deep into this. The whole question of sort of the construction of real numbers, that is, numbers of arbitrary size rather than just integers. And this notion, people would say, who was it? I think it was it Dedekind or somebody else? Says, integers are kind of the work of God, real numbers are constructed by humans. I think I am increasingly having a better understanding of what the foundations of math should be thought, how they should really be thought about. There's something that's very recently emerged for me as a result of understanding the relationship between kind of the fundamental structure of the physical universe and the fundamental structure of the meta-mathematical universe, something I've recently been understanding, and I might take a somewhat contrary view there. But the concept of how do you really construct a real number, you might say, oh, it's really obvious. You just pick a number. You can type in any number you want. Well, it's not quite as obvious as that, because, for example, one of the big issues is 0.999999999 with all the nines equal to 1.00000? Is it equal? Is it not equal? Not clear. Those two things are probably considered equal, even though they're represented differently. That's the beginning of a whole series of complicated issues about real numbers and about exactly how they're defined. And for example, if you are presented with two real numbers, one of them is square root 2 minus pi over some cube root of this and blah, 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 blah. You have an expression for that real number. And then you have another expression for a real number, and you say, are those two expressions equal? Well, that may be really hard to determine. For integers, if you're dealing with arithmetic operations, for example, you just do the arithmetic and you get the answer. It's this integer. You're happy. There's just one representation of it. You can easily tell if it's equal. That's not true for real numbers. That's not true for numbers that aren't sort of discrete like integers. You can have these different representations for numbers, and telling whether they're equal or not is really difficult. Now, what turned out to be the case, which surprised, I think, people to some extent, is if you have an equation to solve and you say the answer is always integers, okay, that's one kind of equation. Another thing is you've got this equation and you can say the answer is any complex number or any real number, a number with any number of digits, where the digits can go on forever. Okay, so you might have thought equations involving real numbers or complex numbers would be intrinsically harder to solve than equations involving integers. You would be wrong about that. What Gödel's theorem showed back in 1931 was that, among other things, it took many more steps to get to this point, that integer equations are fundamentally difficult to deal with. It was the late 1960s before it was fully established that so-called Diophantine equations involving integers, that there is no decision procedure. If you ask, does this equation have a solution? It may be arbitrarily hard to answer that. Like you could say, well, I'm just going to try all the numbers, but there's no upper bound on how big a number you'd have to try. And sometimes it might be, a 100-digit number or a 1,000-digit or a billion-digit number. And eventually at the trillion-digit number, boom, you've got an answer. And so for Diophantine equations, it is sort of arbitrarily difficult to answer the question whether there's a solution. In contrast, equations involving real variables, if you just restrict it to square roots and cube roots and radicals and things like that, there is a decision procedure. A chap called Alfred Tarski came up with a version of that in the 1940s, I guess, that there is a systematic way to just grind through and solve any such equation. In fact, in Wolfram language and in Mathematica, we finally made a practical version of that decision procedure that we use all the time to solve those kinds of systems of continuous equations, of real number equations and so on. So the surprise is actually for equations, real numbers are easier to deal with than integers. But sort of definitionally, it's a lot harder to deal with real numbers than it is to deal with integers. And I might say that when it comes to real numbers, the case of radicals is decidable. The case where you can involve trigonometric functions and so on, this question of is there a way to figure out whether these two things are equal, again, falls into the same questions. You can basically encode problems that are about integers there. And again, you have this sort of problem of you might have to do an infinite computation to get to the answer. There was a question here from Erin. What's the largest number that I've ever used in practice in a computation? Well, I can tell you I've encountered some pretty big numbers in my time. So there's some stuff I've been doing recently having to do with this problem, Emil Post's problem of tag, where we're just trying to work out, does this thing halt or not? And it's been spending a lot of time on computers, and it's routine to get to 100 trillion. Now we're getting 100 trillion steps, and we don't know if it halted or not. So I've certainly encountered numbers of that size where I care about every last digit of the number. Now, another thing that's happened is that I've ended up with a bunch of numbers that are generated by tetration. So if we go, you add ones together, you get, let's say you repeatedly add numbers together, it's like multiplying numbers. You repeatedly multiply numbers together, it's like taking powers. you repeatedly take powers of numbers. It's another kind of operation, sometimes called power towers, sometimes called tetration. It's where you get things like 2 to the 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 2, et cetera, et cetera, et cetera. You get those kinds of towers. Yes, I have encountered such towers. Those have arisen quite naturally. There are very simple systems that involve just doing simple sort of symbolic transformations that immediately give you these tetration type numbers. And those numbers can be extremely big. They get, and I've tried to figure out even approximately how large the numbers are, and even that you quickly run out of being able to say what are even the first digits in those numbers, and that those numbers can be represented as 10 to the 10 to the 10 to the 10. You don't even know if it's 1.5 times 10 to the 10 to the 10 or 6.7. You can't find those leading digits. Actually, strangely, you can find the trailing digits often, but not the leading digits. So those are places where I've run into some big numbers, and where another place where that happens is the halting of Turing machines. There can be things where you can say this machine will halt, but it only halts after this absurdly long time that is defined by this number that is represented in terms of things like tetration. Okay. Let's see. Brian is commenting that moving from Roman numerals to Indo-Arabic helped merchants back in the day. Absolutely. That's how. That's sort of why Fibonacci was sort of a hero at that time. Jonas is asking, was tau used before pi? I don't think so. So tau is pi over 2. Like it's like if you draw a pi, it's one part of that. Yes, it's pi over 2. And there's a kind of a question. We were wondering at one point, if you look at all the math formulas that people write down, does pi usually occur as pi over 2, or does it usually actually occur as pi? And I'm trying to remember the answer to this. I think it was not. Pi over 2 is definitely less common than just pure pi. Pi, there's just all kinds of different reasons in math why you end up with pi. And there are, some of them lead to pi over 2, but many of them don't. There's Pi Day. March 14th is Pi Day, 314. And there's also Tau Day, whatever it is. Just Tau Day. I thought it was 157, but that can't be right because, anyway, never mind. There's a Tau Day. Or am I confusing myself here with in any case, the thing that so we tried to do this study for one of these Tau days, and I don't think Tau was the winner in that case. So I don't know. Certainly, the notation of Tau for pi over 2 is a modern, recent Qt notation. Let's see. Oh boy, there's all right. There's a question about well, why not? David asks, did Feynman overestimate Fredkin? Have string theorists underestimated Fredkin? So this is complicated because these are, I can tell all kinds of stories about people who've been dead for 100 years. It's less clear the extent to which I should tell stories about people who are, alive and friends of mine and so on. But Ed Fredkin has had an interesting enough life. I think it deserves to be told a bit. And so Ed has been a big proponent of kind of digital physics, and kind of somehow physics is computational. And he's had an interesting life. And sometimes I've known him for, 40-something years now. And sometimes I will admit, and he certainly knows I think this, that I find his work a bit frustrating because it's like he's never really, studied, in my own life, as I've come to sort of understand physics as a very computational kind of thing, that was a kind of second act for me. Back when I was much younger, I did physics the same way most other physicists do physics, using standard mathematical methods and so on. And well, I used computers, which was a little unusual, but basically doing physics the way that people have learned physics for the last 100 years or so. Ed has never really went through that. And so for him, it's like, can I find an electron in a cellular automaton? Maybe there's a way that this cluster of bits in a cellular automaton is like an electron. And it's like, Ed, that just can't work that way. We know enough about physics to know that's not how that can work. Now, there may be interesting ideas there, and Ed has had a bunch of interesting ideas about sort of what computation makes possible, but this kind of very direct, I see this thing moving across the screen, it must be an electron. I don't think that works. It's more subtle than that. There are more layers than that. It's not such a direct kind of correspondence. But Ed's own history, I think, is interesting. I see if I can, he must have been, let's see, he's now 80-ish. So he grew up in New York City, and I think his father was actually something of an inventor and polymath and writer of books about the nature of the world and so on. But Ed himself wound up as a student at Caltech, but dropped out fairly quickly and joined the Air Force and became a test pilot. And he has many stories to tell about test piloting, which are quite fun. But then he kind of sort of in the Air Force, he got assigned to be involved with the early air defense computer systems. This was in the 1950s, and this was out at Lincoln Labs in Massachusetts. This concept of using that's like aggregating all the data from radar and so on, and making them and that was the early things like the SAGE system that was for sort of aggregating command and control air defense type things. I think the thing that wound up in Cheyenne Mountain in Wyoming, right? That's this big facility that's sort of carved into the inside of a mountain, able to withstand, the most intense nuclear war and so on. I think its main technological feature is that the whole facility is on a giant spring. So even if there's a big nuclear explosion somewhere on the mountain and everything kind of has a giant earthquake, the computers will be okay. I mean, I don't know whether they're still running the computers from the 1950s. Somehow the way these things work in some of those areas, there's sort of a 50-year procurement cycle or something, and it maybe they still are. Probably they're not anymore. But anyways, in any case, Ed got involved in the programming of those early computers, which was not really a thing in those days, and they were kind of like IBM had been the main producer of those computers, and I think they sort of trained some people from the Air Force, and Ed was one of them, how to program the computer. I think then Ed left the Air Force, got involved with this company called BB&N, Bolt, Beranek, and Newman, which was originally, I think, primarily an acoustics company, but became very much a computer-related company and was notable for having been a key part of the development of the ARPANET that became the internet and so on. So then Ed, I don't know all the details, and this must have been 1960, very early 60s. Ed kind of left that, went to Los Angeles and started a company called III, Information International Incorporated, which was a very creative early kind of computer company, which did early computer graphics, like it made the CBS rotating eye graphic that they used as a sort of, I don't know what they're called, but the thing to start programs and so on, that was made originally by III. And III had a very creative group of people associated with it. That was kind of Ed's thing. And he had a partner in that, and I think the partner died, and that caused the company to have all kinds of problems. And Ed kind of left that, having made a certain amount of money from III. One consequence of which was that he bought himself this island in the British Virgin Islands, and I think his theory was, this was 1960, mid 1960s, And most people's theory was the world's going to end in a giant, World War III nuclear confrontation. And Ed had figured out that the wind patterns of the Earth mixed least if you were near the equator, like in the Caribbean and so on. And so you would be okay, and there wouldn't be much nuclear fallout there, even if the northern hemisphere blew itself up with a nasty exchange of nuclear weapons. So he decided he was going to buy himself this island. I suppose in today's world, people are keen on New Zealand and places like that as the out of the way places to own real estate and so on. But anyway, Ed was sort of innovative and in this, and got this island called Mosquito Island in the British Virgin Islands. And I visited there only once. It was in probably 1983, maybe 82 perhaps. Yeah, I think 82. It had many interesting features it had a certain the kind of the James Bond villain living on the obscure island type thing definitely had its resonance with some aspects of that situation. But in any case, and I remember at the time, this was the time, maybe it was a few years after that early, I should tell more about Ed's story because that got into the 1980s, but he bought this island anyway. He finally sold it to Richard Branson actually a few years ago. It's I'm sure now it's probably become a hotel and you can probably stay there. But in any case, back to the story of Ed and his activities. So back in III, he kind of left III, and then he got recruited to be the head of the lab for computer science at MIT. And he was very proud of the fact that he didn't have a college degree. He had no academic qualifications, but yet he was being pulled in to be the head of this computer science operation at MIT. And in fact, he was quite successful at that. He was along with Marvin Minsky and other people, was and that was all connected to the AI lab, and it was kind of these two different pieces. But he sort of successfully ran that for quite a number of years. And one of the things that he was always keen on was he kind of had this notion, and I think he told me he started on this in like 1958, this idea that somehow cellular automata were like physics. And he looked at two-dimensional cellular automata, and he wrote programs for them, I think, on the PDP-1. He at BBNN, maybe 1961, 2, something like that. He was writing programs to do certain kinds of simple two-dimensional cellular automata. And he kind of had this conviction that somehow physics must be like computers, and but like things like two-dimensional cellular automata. When he was at MIT, he would teach classes about this kind of thing and so on. And he also had another idea, which was computing doesn't have to be, could be reversible. You could have something where usually when you have an AND gate or something, it's like it has two inputs, it has one output. Once you have the output, you can't reverse it and say what the inputs were. But what if you had a gate that had two inputs and two outputs? Well, then you could, in principle, if the gate did the right things, you could, in principle, reverse any computation. And so he kind of had that idea. Von Neumann had the idea that every computation must be sort of, for some kind of thermodynamic, must be irreversible. There must be a fundamental irreversibility to computation. There's a chap called Rolf Landauer, actually, at IBM, who was very much into studying that sort of thermodynamics of computation. Between him and a person called Charles Bennett, also at IBM, and Ed Fredkin, that kind of crowd by the 1970s had sort of convinced themselves, at least, that computation could be reversible. And that's of course true. And now there are Fredkin gates, which people talk about in quantum computing. They are examples of gates. I think they're 3-to-3 gates, if I remember correctly, that have this feature that they can be run reversibly, so to speak. But that was kind of one of the ideas that Ed was like, computation can be reversible. But the technical details of that were sometimes a bit elusive for him, and later on got filled in by other people. But Ed, I guess by the time I knew him, which was beginning of the 1980s, he was no longer so much affiliated with MIT, and he had become involved in investing in lots of companies. And there was one in particular that was a workstation company that made a machine called the PERQ, P-E-R-Q, which was an early workstation computer. This is back in the early 80s. And I remember that one of the more amusing features was that this was a British company, I guess, is that right? It somehow had some, it must have been a Boston-based company, because it was the Three Rivers Computer Corporation was I think the name of the company. And I think it was Boston-based. But that's right, it made this big deal with the British government to supply PERQ computers in the UK. And that was something Ed had been much involved in. But one of the sort of footnote features of the PERQ computer is operates at 100% humidity, can be used on a tropical island, the British Virgin Islands, without all the electronics, shorting out and so on. And that was kind of an Ed special feature of that computer, and also ran cellular automata very nicely on a nice bitmap display. Well, in any case, subsequently, Ed, Dick Feynman always used to enjoy Ed, because Ed is he's a colorful person who tells many colorful stories, some of which are even correct, and has many kind of wild ideas, so to speak. I would say he's been a user of our language since it began, and he's always coming up with, you should do this, you should do that. And they're always very, let's say, it's like, well, yes, yes, we could do that. It will take 20 years to do that, Ed. It's a big, difficult thing to do. It's not just one of these, oh yeah, well, we'll happen to do that. And usually the things were sort of going in that direction and so on. But I certainly think Ed is very much on the sort of the big ideas direction of things. But I remember some years after that, being in the slightly peculiar situation that Ed was becoming a visiting professor at Boston University. And so I got roped in to write a recommendation letter for Ed. And I seem to remember that I wrote something like, he's not, has all kinds of interesting ideas, but you must recognize that he is much more used to boardroom presentations than academic lectures. And so his style of presenting is not what you expect of an academic. Actually, I remember back in the early 80s, I remember Ed wanting to make some deal with me where I would teach him how to write an academic paper and he would teach me how to run companies and so on. We never executed on this deal. It turned out I seemed to figure out more or less how to run companies, and I kind of stopped writing academic papers. So I perhaps wouldn't have been the best tutor on writing academic papers. But anyway, so that's a little bit on the story of Ed. I mean, in a sense, Ed has pushed for this idea of, the universe is like a cellular automaton, which I just don't think is correct. But the idea that the universe is somehow fundamentally computational, I do think is correct. And I have to say that in some ways, the pushing of what I thought was an overly simplistic theory probably slowed some things down, for me at least, for a number of years, because it's like, no, that isn't right. Let's not go down that path because it's just not right. And that, understanding that the story that we now understand about these kind of hypergraphs and things, which are much floppier kinds of structures than the rigid grid of a cellular automaton and so on. But I think Ed has some, unfortunately, he's, as will happen to us all, I suppose it should happen to us all, gets old, but I think Ed has an awful lot of interesting stories to tell about, Ed, because of his role in the Air Force, he ended up starting an air taxi service. And one of the things that happened with his air taxi service, he had all kinds of interesting clients. And so Ed would, I guess, when sort of things fell through for his pilots, would be flying the planes himself. And he has just an awful lot of interesting characters who he met through running an air taxi service in the New England area, so to speak, and then being consultant for IBM and Digital Equipment Corporation and so on. And just a lot of interesting stories about the history of the computer industry. And in some cases, things where Ed will certainly tell stories about how various critical decisions made by these various companies were either followed Ed or more likely didn't follow Ed, but should have followed Ed, so to speak, in what he told them. And it's often hard to tell, when you advise some company, particularly a larger company, and you're like, I told you to do this. And then 5 years later, well, they do that or they don't do that. It's like the connection between what you said and what they did is often extremely hard to trace. But they're sort of interesting stories there. So, okay, there are a few other questions. Let me, oh, you see, look at this. Somebody is pointing out tau day is June 28th, 628. So I got this wrong. Tau is 2 pi. Why does that make sense? I thought tau was a half of a pi. My apologies. I hope I was at least clear on the fact that I wasn't clear in describing that. This question from Philip here. Did I work much with Murray Gell-Mann? Any shareable stories? Well, yeah, I knew Murray Gell-Mann quite well, I think. I actually wrote a piece, sort of obituary piece about him that probably has more detail than I'll say here. But Murray was, for me, in some ways, a very frustrating character. A great physicist who had done his great work quite early in his life. By the time I knew him, his great work was kind of in the past, as it turned out. I mean, I first interacted with Murray when I was probably, 17 years old, I think. And I was in England, and I was sort of going to go to graduate school somewhere. And I get this call one day from Murray Gell-Mann telling me, oh, you should come to Caltech for graduate school. Well, in those days, it wasn't like cell phones. It was quite coincidental that he actually managed to successfully, find me at a phone that could be called at. But anyway, he did. And I have to say, I remember that conversation as being, I think Murray was a little bit perhaps put out that he expected me to be a little bit more sort of starstruck by the fact that he bothered to make the phone call than perhaps I was, and maybe I was too bratty, a 17-year-old, I don't really know. But that was my first encounter with Murray. And then, so I did go to Caltech for graduate school, a few months after that. And I remember the first time I met Murray was, a few days after I showed up there. And this is very typical Murray situation. Okay, so there I was, and Murray, wants to say something. Sort of, he says, "It must be a tremendous culture shock coming from from England to California," and then looks at me and realizes, I'm wearing this bright yellow shirt and these sandals and things, and I'm kind of looking very indigenous, so to speak, or very at least Californian at that point. And so he's then it's very typical Murray. I mean, he kind of is sort of embarrassed. He said the wrong thing, and then goes off in some other direction. But I mean, Murray was was somebody who just had done great work in mathematical physics, inventing quarks, inventing strangeness, figuring out, sort of really pushing gauge theories early on. But then somehow, I think to some extent, the kind of, when I knew him, sort of the years when he was the absolutely golden person of physics, where basically every major idea in physics came from Murray, those ideas had passed, those years had passed. And he never really managed to get a good second act. And I think it really upset him that he wasn't seeing, what does he do next, so to speak. And so, when I knew him, he was quite bitter, I would say, about a lot of the, people don't understand that Murray, had done this and this and this and this and this, which he had, but, the nature of sort of the academic enterprise tends to be rather unforgiving about those kinds of things. And I think, I remember, but Murray would do kind of silly things. Like I remember one time I'm talking to him about this thing called the beta function, which is a feature of quantum field theory. And, it's like the name this was in 1978 or something like that. People would call the beta function. That was what it was called. Okay. Well, it turns out, and I knew this perfectly well, that Murray had written an early paper with a person called Francis Lowe back in maybe 1956, where he had introduced a version of the beta function, but he called it the psi function. It had a slightly different definition, but it was, the sort of the effective equivalent of the beta function. Okay, so we have this whole long conversation where Murray is pretending he doesn't understand a word I'm saying. I'm talking about beta functions and this and that and the other, and eventually Murray says, "Oh, you mean the psi function? Why didn't you just say that?" And it's like, look, yes, I mean, I understand that and perhaps, perhaps in more modern times, I would have made that clarification for him, but he knew perfectly well what I was talking about and had known from the beginning of the conversation, but was just kind of doing this kind of branding presentation, so to speak, about that. I think, so, he could be a bit frustrating in those kinds of ways. I would say that his, later on, he he was much involved with the Santa Fe Institute and the whole sort of complexity direction that I had kind of, I think, initiated for those guys. But Murray really took that on in a very sort of serious way and was like, complexity is everything and so on. And I would try to talk to Murray about this stuff. And he'd known a bunch of the work that I'd done in the 1980s about these things. And we talked about it a bunch of times, although he never really seemed to care that much about it. But by that point, Murray was sort of working on complexity and hoping that the sort of golden touch that he'd had in particle physics back in the 1950s and early 1960s would somehow would somehow adapt itself to complexity. And it just wasn't working. It just was like, let's make a definition of the concept of complexity using mathematical physics. It just doesn't work. It's a different kind of thing. And it didn't help that Murray tended to be very judgmental about lots of kinds of things. For example, one of his probably less endearing features was that, he would talk about physics. There's particle physics. That was the thing he was really big on. And there's what he used to call squalid state physics, which meant what's now called condensed matter physics, used to be called solid state physics. But he would always call it squalid state physics, which was seemed like a needless kind of poke. And I think that, and that was kind of, again, quintessential Murray. But I think that and Murray would be Murray was a very erudite person, particularly interested in kind of human languages and things like this. And he would always, he had the misfortune of working, basically right next door to Dick Feynman. And the two of them, they had a very frenemy type relationship. I mean, they had done some work together in the 1950s that was quite successful, but then they were, always at each other's throats. I mean, each of them told me terrible stories about the other one. And, I think Murray was just, Dick Feynman was always, kind of playing the, oh, I'm just the simple guy from the Bronx or whatever. And they both came from New York City, but in the New York City area. And Murray was like, I'm the sophisticated, pronounce every foreign word correctly. And Feynman was always I'm just going to say it the way I think it should sound. And I don't care about all this erudite stuff. And so that led to quite a tension there. But, Murray would have this feature that, and again, it was very, very badly conceived for Murray, given his personality, that, he was very into words. And when he would meet people, one of the things he would always do is try and explain the origin of their names. And this is just such a bad idea, because if there's one word or one thing where you're likely to know something about the history, it's your own name. And so he would, I saw many of these cases where he would be telling people, your name is a version of something in, High Slavic of this, that, and the other. And the person will say, Murray, that's just nonsense. my name was made up by some immigration official at Ellis Island, 2 generations ago or something. And then Murray would be very kind of embarrassed. And it was just a very terrible situation because he kept on setting himself up for something where he would be embarrassed by sort of not being by not knowing what was going on. And I think in his later years, he worked, he was very much involved with the Santa Fe Institute and worked on complexity. And there was a sort of terrible thing that happened because he was going to write a book, which was, I kind of hoped would be an autobiography because I thought there was a lot of really interesting material. Murray was a perfectionistic writer. It took him a very long time to write text. The text he wrote have a habit of being a bit wooden through over rewriting, I would say. But he set about writing this book, but he said, no, it's not going to be an autobiography. It's going to be a great book of new science. The problem was that he didn't really have the new science to feed into it. He went through a couple of editors. He said it gave him a heart attack, doing the sort of the stress of trying to do this book. It had been set up by an agent we both know, both knew, who had got him a big advance for this book. And so he was like committed, he's going to write this book. And what's the book going to be? And I was like, for goodness sake, make it an autobiography. That's the book that you should write. But no, he wanted to write a book of primary science, and he in the end wrote this book called The Quark and the Jaguar, which I'm afraid is not a terribly good book, and and that was and it sort of almost killed him writing that book, which is just a bad story. And I think he did things like, again, typical Murray. This was told to me. Originally, I was tipped off to this by a person called George Zweig. George Zweig, longtime friend of mine, was the other inventor of quarks, along with Murray. George had been a graduate student at Caltech and kind of came up with the sort of idea of quarks, sort of independent of Murray, and there's kind of a long time story between of what happened there. But anyway, George tipped me off to the fact that Murray had told him, I'm not putting people's names in the index so that they'll have to read through the book to find out if they're in there or not. And that was, of course, now that there are ebooks, it's a bit of a different story. But that was sort of, again, a typical kind of strange Murray move. But in a sense, Murray was, he also tended to have a habit of, he would glom on to particularly people who he thought were, promising. And unfortunately, his choice of promising people and his choice of people who he thought were unpromising turned out to be often very wide of the mark. And for example, a number of physicists, Steve Weinberg is one particular one who comes to mind. Murray was like always, attacking, he doesn't have anything to contribute. Well, it turned out he contributed a lot. Maybe he's I'm not sure I always agree with him, but he certainly contributed plenty to physics. And then Murray would be very keen on these other people who never really went very far. And I was a bit afraid because Murray was always a big proponent of mine, and at least in the early years. And so I always thought that was a little bit scary because it's like, I look at these examples of Murray has been a big proponent of this and this and this, and they didn't work out very well. But Murray had many things Murray invented. Not only quarks and strangeness, he was also very involved in QCD. The detailed story of the origination of QCD is kind of complicated, but Murray was definitely involved. String theory to some extent also. To some extent, that's again a complicated story. He long supported John Schwartz, who was sort of one of the people who kept string theory alive from its origination in the 1960s to its kind of rebirth in the supergravity world of the when was it, mid to late 1980s. So in any case, that was but yes, I would say. I could tell many more stories about Murray, but I would say that one of my personal takeaways from Murray is, it's cool to have successes early in life. in science or something, the management of a career after that is a difficult matter. And it's something where I always felt Murray had really wanted a second act. I mean, he became, he was on corporate boards and he would try to be sort of a poobah of science. He wasn't terribly good at that because he would tend to be rather opinionated. Many of us are opinionated, but, the question is whether we put ourselves in situations where that is not really what's wanted. And Murray did. And so people would be like, oh, no, we don't want Murray involved in this thing. And then Murray will be all upset because he felt he was being rejected from this thing and so on. So it was a he never really found a great second act. He was a very, his erudition was, there should have been a second act, but he never really quite figured out what it was. And perhaps if he had been a less labored writer, he would have been a sort of a great writer of grand sort of pictures of science, the arts, and everything, because he had a pretty broad knowledge of lots of kinds of things. He was very into archaeology, very into languages, et cetera, et cetera, et cetera. But somehow he never managed, it's sort of interesting, he never managed to pull together like his knowledge of linguistics and languages as a matter of, this is the pronunciation of this word in some obscure language. That was very good. His knowledge of kind of what's the big picture of how do we think about, how language works and so on. I don't think he ever really got to that. And I remember having discussions with him sort of late in his life about those kinds of things, which, I have a particular point of view, at least from having designed computational languages for a long time. And I think I always felt that Murray wasn't really at the starting gate in terms of understanding the issues there. I'm not sure we've understood them yet, but I just didn't think he was going in the right direction there. All right, well, I should wrap up very soon here. Maybe one last all right, I'm gonna take one last one that's kind of a funky one, which is, what is my opinion on the resurgence of UFOs? That's a fun one. What is my opinion on resurgence? I've certainly noticed the fact that people are talking more about, Air Force sightings of UFOs and all this kind of thing. I think it's sort of an interesting question. It raises all kinds of philosophical questions about what is an alien, is it an alien spacecraft? Does it have to have come from outer space to be a UFO? Does it, if you have some weird new meteorological phenomenon that's never been seen before, how does that relate to being a UFO-like thing? I think that's and that which is not explained, what is its origin? Do you say, this thing we can't explain must be of supernatural origins, or do you say, well, we just didn't manage to figure out enough about science to explain that? That's a continuing kind of question that comes up in lots of places. Now, in terms of this question of sort of what's known in the world and suppressed as knowledge, that's an interesting question. And occasionally, in different countries, there are different rules about, things which are born secret versus things which are only secret if you basically made a contract with the government that says you'll keep them secret. And so there are different things. And over the course of my life, I've certainly learned a bunch of things that, have sort of fallen out of being where I've, they're not things where I'm signed up to keep them secret, but they've kind of fallen out of different kinds of things. And you sort of learn these things which are kind of, knowledge that's kind of been suppressed in some way or another. And sometimes that knowledge is, it's kind of interesting because some of the things I've learned along those lines about scientific, technological kinds of things are like, people say, well, yes, it was kept secret because it's so weird and kind of hokey that, and not about UFOs, but about sort of how various kinds of technologies work and how to actually do this or that thing. Oh, you use some kind of food and you smear it on a submarine or something, and that works great. That's not a real one. That works great as a way to reduce the drag of the submarine or something like this. not a real one. But but nobody. If you told the world, you smear butter on the submarine to get it to go faster, everybody would just laugh at you. So it's better to just keep it a secret. But I don't know the extent to which, that there are these things where there was, something. It's always an interesting question. The things which were over the course of history, and we certainly know them going back, centuries. Things which this was a government secret, so to speak, and what happened to it, or this was, a piece of cryptography that nobody's going to nobody's going to decode that, when, how long can these things be kept secret, and when you decode it, is it even interesting, and so on. So I don't know what I have no profound insight, probably. Although I think it's sort of an interesting question, how much hidden knowledge is there in the world? If you go back N years, let's say you go back 100 years, is there still any hidden knowledge in the world? That is, there stuff that was known to, let's say, governments and so on, but has never been brought out into the public eye? Is there stuff that, if you go less time than that, Second World War time frame, there's still some stuff that's still classified from that period of time. As you go closer to the present day, what's the rate of kind of undisclosed knowledge, so to speak? And particularly when it comes to scientific knowledge, what is there that's disclosed versus not disclosed? And I think, two big areas, nuclear weapons and cryptography, were two big areas coming out of the Second World War. Cryptography kind of stayed secret longer. And, there are pieces, I think, of the story of cryptography in World War II, which are still not, some are only very recently declassified. I remember, just to tell a funny story, perhaps, or an interesting story. So when I was young, Alan Turing was not a particularly famous person. But certainly the work that he did at Bletchley Park during World War II was completely unknown. And in fact, the only rumor that I sort of heard, picked up in the 1970s, was two things. I picked up this sort of rumor, maybe Turing had been involved with Bletchley Park, maybe he invented the codes that were used by the British, maybe he'd been bumped off because they didn't want people to know what codes they'd been using because they wanted to keep them secret. That was that was the rumor mill around kind of the Oxford-ish area. Meanwhile, actually, when I was slightly younger than that, there was a classics professor I knew, an older fellow, who, again, I didn't know what he did during World War II. I only knew that he'd done something notable in World War II, but I didn't know what it was. And it had been something about, writing leaflets. One part that I'd heard was sort of writing leaflets that will be dropped from planes over Berlin to, over Germany to kind of tell the enemy why they're doomed type thing. But in fact, he told me one thing was, he said, oh yeah, there was this chap I knew during the war named Alan Turing, and he's an interesting chap. The stuff you're talking about, it sounds like kind of thing he was interested in. That was one thing. Second thing was, we talked to me about, things about Latin and whatever. And every time the word ultra would show up in any piece of Latin, he would sort of repeat ultra, 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 ultra. Just keep repeating this word. Why? No idea. But I remembered that. And of course, many years later, I discovered, when the whole Bletchley Park story was declassified, there was this thing called Ultra at Bletchley Park. It was a code name, and this guy had worked on that. And this was, he was going to be proper and not disclose any secret to the random 12-year-old or whatever it was. But but on the other hand, he wanted to kind of pass on this piece of knowledge and leave this little piece thing hanging out there, this morsel hanging out there. And he had a correct calculation that I remembered this kind of eccentricity years later. Anyway, I just mentioned one thing. I was at in 2012, it was the centenary of Alan Turing's birth, and there were a bunch of events that were around. That I was at one in Cambridge, where a person was talking about their work at Bletchley Park. And this person didn't know, nobody told them that the work they'd done had been declassified. It was only declassified in the 1990s. And this person had a whole career in, I think, advertising after their time at Bletchley Park. And by the point that where they were giving this talk, they were quite old. But anyway, they'd worked at Bletchley Park, and they were just describing how, and I think this was the first time they talked about this stuff, because they didn't know. Nobody went back and said, oh, we should go tell all these people that the work they did in World War II is now declassified. But he was working on this this sort of super secret network of cryptographic devices that the Nazis had, not like Enigma, which was quite widely distributed among their field commanders. This was just for sort of central command posts or something, and there were a small number of nodes of this thing. But apparently, due to some clerk somewhere in Greece or something, had resent a message twice, which is a deadly thing to do in the cryptography business. Anyway, they managed to decode this, and this guy was sort of describing the fact that having got to the end of the message, he was decoding pieces of this message, and at the end it says, the message is signed, Adolf Hitler Führer, and that's kind of the that's the point where he knows he's correctly decoded the message. But it's sort of a remarkable thing to have managed to pull that out from this, and then that it was secret that this crypto system had even existed, and second had been broken. It was secret for many, many, many years. And so, there's this whole question about, what is the decay time of secrets? What should it be? That's a different question. What is it? Interesting question. If there are sort of weird UFO-like things that, would they have been kept secret for 50 years, 70 years, whatever it is? I don't know. I think that the number of secrets from World War II timeframe is definitely dwindling to almost nothing in the areas that I'm aware of, like nuclear weapons and cryptography. All right, I think it's time to wrap up here before I say anything otherwise too horrifying. But actually, I'm about to go to my day job, and actually we have a live stream coming up there about Wolfram language design. But lots of questions I didn't get to today, which I'd love to get to another time, and look forward to being with you again for this History of Science and Technology in 2 weeks. Okay, so thanks for joining us.